Okay, in this next video we're going to take a look at really a follow-on from direct proportionality, but we're now going to look at inverse proportionality. So in this wee PowerPoint we'll try and really understand what inverse proportionality means, and then look at various graphs that represent inverse proportionality. Now, inverse proportionality is perhaps a term you have not come across before or heard of before, and we'll see look at it as a little bit more complex than direct proportionality. A simple example using the general speed equation, distance over time, will be used to demonstrate this concept. So similar to the previous videos, you might just want to pause the screen and then copy down the respective notes. So if we take a look here at worked example 1, and if you have to travel a set distance on a journey, that set distance means, of course, that the distance d is going to be a constant. So we know, of course, speed s is equal to distance d divided by your respective time taken. And that's the same really as expressing speed as being equal to your distance. That's your numerator multiplied by 1 over t. So again, we can really expand this fraction as being this numerator d multiplied by 1 over t. Again, because we're traveling a set distance, of course, the d in both cases is, of course, constant. And therefore, we can say that because there's only two variables changing in this instance, that the speed is proportional to 1 over t. So if you just want to copy down those notes, copy them into your notebook, and then we'll continue on. Now, we've just sort of seen in the previous slide that the speed is proportional to 1 over t. We can therefore state the following in relation to this situation. We can say that the speed s is directly proportional to this quantity 1 over t. And therefore, if we were to plot a graph of speed, you can see on the y-axis against 1 over t, you can see on the x-axis, have a little think what that particular graph would look like. So pause the screen, copy down the notes, copy down the graph, and then with a pencil, sketch down what graph you think you would get in this particular situation. Now, because the speed is directly proportional to 1 over t, this quantity is proportional to this quantity here. I think the fraction does tend to make it a little bit more complex for some students. But because these two things, s and 1 over t, are directly proportional, we're really, as per our previous video, if we put these two quantities on the y and the x-axis, then we should be getting a straight line that's passing through the origin. So again, if you need to, you could rub out your graph and then copy down the respective notes if you need to modify the graph and then the notes as well. Now, in general, when a quantity y, any variable that's on the y-axis, is proportional to 1 over x, that's any quantity, we've seen the previous example t on the x-axis, and we can say that y is directly proportional to 1 over x. And a graph when drawn of, in this case it should be really y, it could be s on the y-axis against 1 over x, should of course be a straight line passing through the origin. So if you just want to copy down these notes, perhaps just instead of putting an s there, you can just put in a y to keep it consistent with the equation above. We can also state from this s being proportional to 1 over t that s is inversely proportional to t. And this is really the main focus of this particular PowerPoint. Now what that really means, that s is inversely proportional to t, if we think about the actual equation involved, if your time t increases, then the speed decreases. Alright, so if you think about that in simple terms, when the quantity t increases, the speed s will decrease. And of course, that's the complete reverse that we've seen back there with direct proportionality in the previous video. In a similar sort of fashion, of course, if t was to decrease, then the speed s would have to increase. Again, just in written form. So when t decreases, the speed s must therefore do the opposite. It needs to increase. So again, definitely pause the screen and copy down these notes into your book as well. Now, we do need to sort of be aware of what's happening here in a little bit more detail in relation to the mathematics involved. Now, similar to the previous PowerPoint, we've got our speed, our independent variable. If you're in a car, that's what you can change. And then the time t is the dependent variable. Like your journey time will depend upon how quickly, how high the speed is. And when we're talking about this inverse proportionality, let's think about what could happen. So let's say, for instance, that the speed divides by 2. So you're now traveling down the road at twice the speed from point A to point B. Well, of course, the time of the journey will increase, but you need to appreciate the time will exactly double. So when you divide the speed by 2, t will in fact multiply by a factor of 2. When the speed's divided by some arbitrarily rare value or odd number like 16.2, well then the time will in fact multiply by a factor of 16.2. Let's say the speed increases by a factor of 8, well then the time will decrease by a factor of 8. And let's say the speed increases by 3.67, the time will then have to divide and decrease by a factor of 3.67. So if you just want to pause, again, copy down those notes and those key numbers into your notebook as well. And hopefully after those slides, you now have an understanding of what inverse proportionality means. And we've gone through those calculations to be specific as well. Now the second thing we'll look at now again is some of the graphs involved. So let's look at now worked example 1. So what would a graph of speed against t, time, look like? So I want you just to sort of copy down these respective notes to copy out the respective graph. You'll notice this one is different from the previous example. You've got speed still on the y-axis, but now we have got t on the x-axis. That's different from the previous graph. Note again, we are assuming that the distance travelled for this particular journey is constant, and therefore it's just really these two variables changing in this particular investigation. So perhaps a new page, pause the screen and copy down the respective notes as well. Now I'm going to sort of take you through the process involved here step by step to build out the plotting points and then finally put in really our line of best fit. So if we were to undertake this investigation and plot a graph of s against t, we're traveling at some specific speed. Now, y in this case is just a particular number. So you've got some speed, y meters per second, and that results in you taking a time, x seconds, to travel that distance d for your journey. Let's just say you're traveling 5 kilometers on a particular journey. So again, pause the screen, copy down these notes, and then we'll move on to the next plotting point. Now let's say the person driving the car decides to double the speed. So now the speed increases to 2y, which you can see in the y-axis here. It's important to note really, as per some of the previous videos, if I'm coming up 1 centimeter to get to y, I would of course be coming up 2 centimeters to get to 2y. Now by doubling the value of my speed, I would then divide the time for my journey by a factor of 2, and so we're now taking that x seconds to complete the journey. We're taking 0.5 x seconds. So again, I advise you on the same graph, if you can, pause the screen, add in these new plotting points and the respective notes around them as well. Now, let's just again undertake a similar process. Let's double the speed again. So we're starting off at 2y, so the speed will now double to become 4y. And similarly, because we've doubled the speed, of course we will take half the time to travel that particular journey. So we're going from 0.5x, and we're now coming down to half that value. The journey just takes 0.25x. So again, on the same graph, add in those notes and the respective plotting points as well. just to suppose to go to one further plotting point, let's say again we double the speed again. Now we're starting off really at 4y, and if we double that, we're up now to a value of 8y on the y-axis. But of course, by doing so, we're traveling twice as quickly, so we can really divide the time for the journey by a factor of 2, and that's really taking us down now to 0.125x, and our plotting point comes up here. Again, on the same graph, pause this, copy down the notes and the plotting points as well. Right, at this stage, we've got enough plotting points on the graph. We can then put in hopefully a decent line of best fit. Just make sure it's reasonably smooth. It's not straight lines connecting the axes together. You will lose marks for that in the exam. So make sure it's reasonably smooth, and this graph here showcases what a graph of inverse proportionality looks like when you've got one variable on the y-axis and the other variable on the respective x-axis. Again, you might just want to pause the screen and then draw in your line of best fit as well. Now, just a couple of important notes here. The graph on the y-axis and the x-axis, they do come closer and closer towards each respective axis, but they never touch it for an inversely proportional graph. Each curve is referred to an asymptote, and they approach both the y and x axes, but they never touch it. So if you're an examiner, you do not want to see this point touching the y-axis. You do not want to see this point touching the x-axis. If they do, it's probably a -2, two mistakes there, and you've just dropped a couple of handy marks. So again, pause the screen and just copy down those respective notes, please. Now, just a bit of a hint here in relation to what I would advise to do. So, keep the start of your graph and the end of your graph at least 1 centimeters away from the y-axis. So this wee plotting point over here, like make sure you're coming out at least 1 centimeter off the vertical axis here, and make sure you're coming off the x-axis by at least 1 centimeter down here as well, just to make it pretty obvious to the examiner that your graph's not touching. You don't want a situation whereby your graph is getting within 1 or 2 millimeters. You don't want to put the examiner in a position of having to zoom in really close to the computer screen to see is it not touching. Again, you're really at risk of losing a couple of handy marks there. Also, make sure whenever you're doing graphs to use a pencil. If you make a mistake, you can then rub it out, and of course you can have a go at doing it again. So just copy out those wee general hints, and more importantly, make sure you adhere to them when you're doing your exam papers. Now, just in summary, when we're dealing with inverse proportionality, again, we're sticking exclusively to this sort of speed equation here. When you've got a graph of s against 1 over t, that could really be any variable y against 1 over x, and those two things are directly proportional to each other. It's a straight line through the origin. When you double one, you double the other. When you don't have this 1 over factor and you've just got s, that could just be the variable y, and it's inversely proportional to t in this case, or any variable on the x-axis. That's the shape of graph you have. You don't have to, of course, put down all these respective numbers. It's the general shape of the graph that, of course, they're looking for in the exam, and then just making sure, again, they do not touch the respective axes. Now, if you feel it would be useful, you could pause the screen and just copy down these two summary graphs, highlighting exactly what's going on inside this particular topic. And that really completes the sketching of the two graphs required for inverse proportionality, and that's us finished up this particular section as well.